Hello and welcome everyone to this presentation on the insights that I have gotten when working on a research project regarding mini-batch alignment for Wi-Fi-CSI data domain fact independent feature extraction. Um, Today I will first briefly explain what the problem description entails. Then I will dive a little bit into the state-of-the-art research that has already tried to solve this problem. Then I will briefly talk about the caveats of the state-of-the-art research and the connected point of focus regarding our research is. Then I will explain what the architecture looks like and how it is trained. And lastly, I will identify the architecture problems that we found and that also resulted in this architecture not performing its intended focus. And we will lastly dive into some of the future research directions that can be followed. So for example, looking at radio signals are influenced by factors that pertain to a specific interest. So for example, when I move my hand into a certain direction and I have a transmitter and receiver in the same area and they transmit signals from each other, my hand will cause certain power attenuation and phase shifts at the signal that is received at the receiver. And as a result, based on these phase differences and power attenuation, you can basically measure if specific activities or gestures have been performed. In addition to the factors of interest, there is also a lot of domain influence imposed on these radio signals. So, for example, a specific lamp or specific piece of furniture in a room will influence the way that radio signals propagate through space, but also the humidity in a specific room will cause this. The way that we see this back in the data used to train deep learning models is that data distributions, especially in the intermediate representation, are unaligned. So, for example, when I do classification and I train my model, I get specific distribution pockets in the intermediate representation. However, when, for example, I take another data sample from another domain and I use that to inference, that data sample might end up in an entirely different space of the intermediate representation, and as a result will be misclassified. And the eventual effect that you see at the end of training and testing is that there is a reduced performance on the test or validation subset if not handled, which can be seen in the image down right. So regarding state-of-the-art research, people have been trying to increase the amount of data in the training phase because more data leads to less chance that data will end up in a wrong region. However, this is not always optimal for every setting, especially settings where people do not have access to a lot of training data. Secondly, people have also tried to use feature selection. However, the problem with feature selection is that it requires a lot of domain expert knowledge. And it has been shown that if deep learning models are complex enough and they have enough expressive power, deep learning models can actually outperform these type of features. Regarding deep learning, there are mainly three different avenues of research at the moment going on, of which one of them is training adaptation, in which you try to align a source and target distribution. An example of how this has been used in the realm of Wi-Fi-CSI is that researchers have basically invented a network that can jointly train a decoder and a task classifier based on a switch between the use of a classification loss, but also a reconstruction loss, which is trained sequentially in one training step. And people have also tried to use adversarial training, in which a discriminator and a activity recognizer play a min-max game against one another, in which you try to shift the latent distribution in favor of factors of interest. Lastly, researchers have also tried to use attention, which basically prioritizes features from the input samples, but it has also been used to correlate temporal features in the intermediate representation. Lastly, people have also tried to use combinations of NAS, neural architecture search, and reinforcement learning, and this is also shown to be favorable for learning features that do not depend on specific domains in which these features were measured. Our research point of focus is essentially on adversarial training. As already discussed, we think that feature selection is not a solution at this point because of the things already mentioned. What we see is that an extensive number of domain labels are required in order to actually train this model, which is not favorable because in addition to the task labels, you also need to create domain labels. And in addition, what other researchers have shown is that if specific factors are not taken into account, so you assume that they do not exist, you see drastic training accuracy drops. And so a potential solution to this is basically to remove the need for domain labeling in the realm of adversarial training, and potentially to add automated incremental learning later on when there is a solution that does not require domain labeling. So this brings us to the architecture that we have created called mini-batch alignment. Mini-batch alignment is essentially a simple activity recognition system that uses a training phase in order to tune this model, train this model towards being able to predict gestures. So first, we pre-process the data into Doppler frequency spectrograms, which essentially explain the amount of motion within specific Doppler frequency regions. These spectrograms are fed into a convolutional neural network consisting of mobile net blocks, which are essentially a more efficient version of normal convolution operations. And later on, in addition to the activity recognizer output that predicts labels, we also have a similarity discriminator that outputs similarity scalars. Similarity scalars are created via two layers called the probability density function estimating layer and the bilinear similarity layer. The probability density function layer measures one-dimensional probability density functions per feature in the intermediate representation, and basically creates a certain set of new edited probability density functions via diffeomorphisms, which are smooth and differentiable functions that can basically edit the probability density function. And these edited, but also the measured probability density functions and also probability density functions from previous seen batches are fed into a bilinear similarity layer, which basically measures the extent towards if specific probability density functions are similar or not based on the current estimated probability density function. And this will result in a set of similarity scalars that are later used to create a similarity loss. And the goal of this model is basically to forget that there are differences between, let's say, the current probability density function and probability density functions seen in previous rounds. And the idea behind this is that this model then, in a similar fashion as the discrimination, the old discrimination model will also prioritize features that are not dependent on specific domains. The hypothesis behind probability density function estimation is based on trying to reduce the distance between distributions via the maximum mean discrepancy loss. Reason being that the maximum mean discrepancy loss is also a approximation on basically trying to reduce the distribution means between a source and target distribution. And so we asked ourselves, why not try to forget mini batch distribution differences instead of focusing on maximum mean discrepancy in order to reduce the overall distance between distributions. And so the perturbations, as already discussed, are based on diffeomorphisms, and similarity learning is basically done via learning a square similarity matrix that is a specific function that that has the ability to show or capture which correlations are important between the two samples in order to learn the actual similarity. Our architecture is essentially tested against the base architecture. That is basically the architecture that you have seen previously, except no similarity learning is involved. And we have also tested this on a domain classification architecture, which is essentially just an architecture that classifies specific domain labels, which are a unique combination of different domain factors. The experimentation methodology used is basically, we basically used domain factor leave-out subset splitting, which is basically, we basically compute labels based on a system that can figure out which domain factors were used to create which domain based on figuring out this via the multidimensional row major order, because basically we flattened the domain labels, and so you can reconstruct this via when you know the order in which things were flattened. And training is basically done in a random split, because it doesn't really matter. The difference between training and validation is not the most important thing to us. The most important thing is basically the domain shift between training and testing. So we used many batches with a certain batch size in combination with the Adam optimizer in order to train the model. And early stopping is based on the validation subset. And we basically compute different classification metrics, which are accuracy, precision recall, F1 score, and Cohen's kappa, based on the validation subset in order to basically decide when to stop training. But we have also computed this based on the test subset in order to eventually show performance in our presentation. So what we have seen is that in the most favorable case, in which extra discriminator layers are added to the domain classification system, so instead of having 2 dense layers, we have 4. And instead of 1 factor leave-out training, we do 2 domain factor leave-out training. And we see that domain classification outperforms both the standard baseline, but also the mini-batch alignment network. And there are several reasons for this. So one of them is that we may have made specific invalid distribution assumptions, of which one is feature selection bias, which means that one-dimensional probability density functions may not be appropriate enough in order to, or they might not be an appropriate feature for basically mitigating, let's say, the domain effect in specific input samples. And so one potential solution could be to try and incorporate copula functions that explain correlation between many univariate distributions. Secondly, we have noticed that diffeomorphisms, especially in later stages of the deep learning network, have a non-deterministic effect due to deep learning models essentially being black boxes. And so more focus may have to be put on input features rather than intermediate representation features. And a potential solution to this could be teacher-student networks that were envisioned in the visual domain that already do this. Lastly, what we have noticed also is that we do not use any operation parameterization in the probability density function creation layer. However, what we see in the realm of variational autoencoders is that they do require parameterization for random nodes, so random operations in the deep neural network graphs. And so one potential solution to this could be to find a parameterization for the probability density function and quantile sampling operations that do involve a random component up to a certain extent in order to allow valid backpropagation through the network. And lastly, we also noticed that there is a lot of nonlinear scaling. A patch was basically to learn, let's say, univariate probability density functions per feature instead of using multidimensional probability distributions. However, as already seen, this did not do anything regarding the any improvement regarding the baseline. So future research directions in this case include testing potential pitfall solutions, as already discussed before, increasing the number of data sets that have some kind of domain shift present in them, because the number of relevant data sets at the moment is limited to 2, mainly WIDAR and SciFi. And another research direction is basically to extend the research effort that has been put into this research project from Wi-Fi-CSI to the millimeter wave and terahertz wave spectra. And so if you want to collaborate, the names and emails are basically shown here on this slide to the right. And yeah, I will basically take questions now if you have any.